Okay, everyone. For the second talk of today, Jiuya Wang from Georgia will give the first of her lectures, this one on Malle's conjecture.
Thank you very much. So the first talk, I will focus on Malle's conjecture. Okay, this is also almost the start point for me to enter this area. And basically, our question is how many number fields are there? And we need to make this question precise. And usually, when we talk about a family of number field, you want to fix the degree. And moreover, you want to fix the Galois group. And if you do that, then the natural question, precise version of this is you look at the number. Let's say we fix the base field to be just a rational number. Then you look at another field where the Galois group is isomorphic to G, and where the X will be the bound with a discriminant, and we ask how large is this number? Say so that is what Malle's conjecture is addressing. There are constantly questions about this line. So let's be careful so that G, so for us, G is always a transitive permutation group inside S. And where n is the degree of our number field. So what do we mean when we say the Galois group of our number field is isomorphic to G as a permutation group? Well, intuitively, if the first time you think about this, you can take your number field and find one primitive element that generates this number field, and let f of x be the defining polynomial. Of alpha, and then the GQ will permute all the roots of f of x, and this gives you a map to Sn. So this is the image of this map will be defined to be the Galois group of K. You might think, okay, this is dependent on the choice, and group theoretically, there is a much cleaner way to view this permutation action, which is start with your number field and find its Galois closure. This G will be the finite group, which is usually the Galois group for K tilde, and let H to be the subgroup that's fixing K. And you look at G acting on all the cosets of H, and this gives you a G map to Sn, which its action is just the left multiplication or right multiplication, depending on your choice, where N now is the index of the sum. Okay, this is really the convenient one that we work with. But just to make the definition perfect, you want to define this Galois group only based on your field. And for this, you start with your number field of degree n, and it has different embeddings of k into q bar. GQ will act on this set. Well, the action is simply, if you start from some sigma I, that is from k to q bar, and then you can compose with any automorphism of q bar, and this gives you a new embedding of k from k to q bar, which is now defines a permutation image for the absolute Galois group. So it is, we constantly use different perspectives when we talk about the permutation structure for the Galois group. And now it's worth mentioning that though we usually think about the Galois group as a finite group, when we look at the different permutation representation, it will give you different answer. Okay, so for a single finite group G can have multiple permutation representation E, a map from G to Sn, and even multiple ones with fixed degree. So for example, even let's say when G is S4, you can already have multiple different degree 6 permutation representations. So sometimes the notation in the literature saying, oh, we look at the degree n, G extension, that is just very misleading. And but that's sometimes people's convention. The second remark is, even though you can talk about different permutation representation, it has been repeatedly proved to be a helpful way to look at this question is when we talk about with a different ordering. So you can, for example, just choose to enumerate all the degree 3 extensions or degree 6 extensions, thinking about number fields, but it's just more convenient to have one family of object for each finite Galois G. And then when you look at different permutation representation, you are only imposing different ordering on this set. So that is a helpful perspective. And please stop me if you have any questions. Okay. Yes.
Ordering your, are you saying that you consider two permutation representations the same if they differ by like an automorphism of SN?
Yes. So those will be considered as isomorphism. You can So basically, if you start with a permutation representation, you can relabeling of these letters, and those will give you isomorphic permutation representation.
Those count the same.
Yeah, they will be count the same. And then when I say different, they definitely cannot be conjugated to each other via inside the SF. Yeah. Okay. So so the first example is definitely a starting point of the counting anything, which is the quadratic extensions. And this is very elementary. And as we know, if you look at the square free quadratic extension, Q join square root of D, then the discriminant will equal to D if D is 1 mod 4, and 4D if D is 2 or 3 mod 4. This is true no matter D positive or negative. Then when we count quadratic extensions for this question, it is simply the number of E that is square free. Let's say D is 1 mod 4, and the absolute value bounded by X. And you can also add in the other family. Okay. This one is classical, then you can just do it with bare hands very quickly. So if we look at just the first one as example, it is very close to counting just the square free integers. And as Ilya has nicely presented, the counting of square free integers, this one will be pretty close, and you just need to be careful about the extra condition at 2. And you can view this as just counting some integers with local conditions at different p. Okay, what does that mean? It means at 2, D need to be 1 mod 4, and at other odd integers, D need to be not divided by p to the square. Okay, so this is the typical setup in analytic number theory, where D when you put all possible divisors that you can impose this condition, and you first include those, first get rid of those that is divided by, for example, 3 square, and then you subtract those by 5 square, and then you add that back the 15 square ones, and then you can just do your estimate. So this one is fairly easy because we are basically just counting integers. There is a density for 1 mod 4 is 1 over 4, and the density for k to the square is k squared. And this is the number of such integers plus some error term, which is super nice. Okay. And actually, if your k is too large, then there is no counting to consider. You can combine this to get your main term, that is but how do you do that? You just add up those main term up to square root of x, and you also add up the error term to up to square root of x. Down is a Mobius function. This is and we get error term that square root of x. So to be careful when you combine these main terms for small k, you only get a truncated product, but when you compare this constant, we will see another square root of x coming up. Okay. I can expand this part more if someone want to see. But this is all very elementary, and this way is called sieving. And we are adopting the mode that I mentioned previously. Basically, the approach where you can forget about all the previous information, just starting from here. And any local information you know from your set, you combine the local information together and you get this. Yes.
Hey, can you put the number 4?
Okay, sorry. Yes, thank you. Okay. And so I would say, we used one local information can be obtained, but maybe no more. And this is exactly the approach if you would like to generalize to other groups like S3, S4, S5. There are many more contents towards those more complicated non-abelian roots, but this is the flavor of the approach. I would say this is more. There is more elegant way to look at this question, which is close to the approach area just mentioned for the square free images. Okay, so we want to understand these partial sum for this Dirichlet series where AD is a number of discriminant with exactly with discriminant capital D. And then we actually know that this one pretty explicitly, because for every fundamental discriminant, you only have one quadratic field, so that is very convenient. And you can write it down that this is 1 if D is 1/4. There's a slightly subtlety here, which is okay for D. That D can be positive. Okay, so our D is absolute discriminant, so it is always positive. But the field that it represents can be positive or negative. But if your D is 1/4, you always only have 1. And if D is 2, okay, if D over 4 is congruent with 2/4, then this is also this is a 2. And if D over 4 is 3, it is 1 or 3/4. This is 1, and D over 4 is well, wait. Okay, this is 2. Sorry, this let's see if is yes, it is a 4. Okay, so you need to do a little bit of thinking, just because the field can be both imaginary or real. So when D is 1/4, negative D is 3/4. So that's why no matter D is 1 or 3/4, you has 1. And when D over 4 is 2/4, it represents 2 of these fields, which is 1 positive, 1 negative. And when D over 4 is 3 or 1/4, then it represents one of these fields again, because yeah. So when you look at put all these together, you get something pretty explicitly and nice. Huh? Pardon?
Is that possible? Because you have quite a big one.
Yes, and then the negative for the one, for the negative one. For the negative one, yes. Okay. Then so yeah, it just needs to do a little bit careful thinking. Sorry. Oh, I definitely mean this is 2. Okay. Okay. I'm sorry if this is a little bit confusing, but starting from this, you can totally be confident about this kind of expression. Okay, so and now following from the alias introduction of these Tauberian theorem, you can now compare this with some nice data function, and by you get an order one simple power at s equals 1. So that's why you don't get the log term. And this is the simple algebraic way. Basically, it is still analytic, but we have this nice covariance theorem which package all the analytic thing you need to know. So then what you need to do is just this algebraic understanding of the quadratic extensions. Okay. So that is the first example. And now we would like to look at the second example. I should say that comparing to these more stealing idea, this is adopted especially when you have very good understanding of the set you want to count, where you can form a explicit generating series, when you know more about the structure for the family. And this is the approach that we are going to adopt once this kind of information is available. So next, I'm going to talk about how we generalize this idea of quadratic extensions to abelian extensions. So what do we need to know? Okay, we need to understand the structure of abelian extensions and over Q. This is very, very explicit. It's just you include all the roots of unity, right? And in fact, you can understand the Galois group of this fairly that is just the zero product of all the Q joints that appear there, P to infinity. And this Galois group is equal to star. So you have the total universe of abelian extensions. As if you star. And you also understand the ramification of this extension because this is the only part where P is ramified, and it is totally ramified. And its inertial group is exactly this ZP star. Okay. So now you can just form your partition of abelian extensions. So A is in bijection to the surjection from a universe to A. Okay, and I should say here, maybe up to some polymorphism. But this is something very explicit, understandable. And remember, we when we talk about counting extensions, we always needed to fix a permutation representation. And for abelian group, there's only one that we can talk about, which is the regular representation. Okay. Now we would like to understand all the all the billion A extensions. And to understand that, we can build this organization just to understand all the suggestions and understand the discriminant. So how do we study the discriminant? Well, you just need to understand what happens for your inertia group. Okay, so to determine homomorphism from this universe to A, this suffices decide how to map your ZD star, which is your inertial group. And there are different cases. If rho P is trivial, then this means your extension is unramified, so you don't get any discriminant there. And the second case will be when the image is not divided by P. And this is what we see tamely ramified. And in this case, you will be able to decide the discriminant completely, because suppose this is your BM extension, you can do the completion, and it will be a direct sum of a bunch of local extensions, and the discriminant A locally is just the product of discriminant locally at different primes above P. And for tamely ramified extension, you have a you can always find a maximal unramified one in the middle, where this is going to be our F and this is going to be our E, and the discriminant will be F times E minus 1 for all of these primes. Okay, and this equals T to the N minus the sum of the inertial degree, and this equals N minus G times F, which is N over E, and this is going to be the number of orbits of your inertia element, inertia. Okay, maybe I should just say inside Sn. Okay, this is just the number of orbits of the inertial group, and for tamely ramified extension, there is only one. This is a cyclic group. There is only one generator, so it's supposed we call the generator YP. It's the same as talking about the number of orbits for this one single group element inside this. And there is the last case is when you have the one ramification, and this will be some subgroup inside A. So this only happens rarely. Only when P divides the size of the Jiuya group question.
Are you saying that EP is the number of orbits of the inertia group, or N minus N of EP is the number?
Oh, yeah, I definitely mean this one. Thank you. Okay. So this happens rarely. We can understand what they are, though we don't necessarily need to be that explicit. And when you gather all the informations, then you can form your generating series. So and since you are free to do anything locally at P, here I'm not encoding the surjection, just a homomorphism, then this is your generating series. And now, since our discriminant can be explicitly described by what we choose to map ZB star to, this is just now the element Y inside A. Discriminant, and we will now where we define the number, n is the degree of our extension. Question.
Yeah, need a rho to be subjective.
We need rho to be surjective. We will come to there soon. Okay. Well, this you also need this to be legal. So when you have CV star mapped to A, and the P is not showing up in the image, this is really a map from FP star to A. So I should say.
Sorry, rho is subjective, is rho P subjective?
Pardon?
So like the rho that has to be subjective, but the rho P that doesn't have to be subjective?
Here everything is not subjective.
Okay.
I'm not importing subjective. Yes. Okay, so where the right. The plainly ramified since we don't allow P to contain in the image. This is a map. Now factor through FP star, so you will also need the order of Y to be be dividing P minus 1. So okay. So that is all you need to do to form the homomorphism. And before we transform between the homomorphism and surjective homomorphism, let's first look at what this series give us from Alias talk. Okay, so roughly speaking, this up to homomorphic should be Y. That is all possible element in a given group. and P, where the order one is dividing P minus one. And where these Y will look is minimal in A, so those will be contributing to the first pole you can ever have with a series. And now we want to count the number of poles, the order of poles. Order is, so how do you think about the order poles? We have the zeta functions that give you one order one pose. And when you look at these, you can compare to the Riemann zeta function, but only for some subset of primes. And if you look at the density of P satisfying this condition, that will be 1 over the size of the order of Y. And so the intuition is if you have density, some fraction densities, then that will contribute the same fractional of the order of the pole. So this will tell you that the order pole should be the index being minimum. Okay, now we want to count the number of which fraction. Fraction will be the density of P that is function of 1, not the order of Y. And then, so how many here is just the number. Okay, I should, okay, so there's no, I should erase the summation there, which is, okay, that's everything. And when you, okay, so this, you observe that this density is exactly the giving you the index of the cyclotomic action of the GQ on this element Y. Okay, so this is staying in it's just the multiplying, it's just the powering on these elements. And this is the orbit stabilizer formula tell you that this is a number of this cyclotomic action of GQ on the set of element with minimal index. Okay, so this is how you get the homomorphisms, and to get the surjective homomorphism, you just need to look at the following. So since the homomorphism is just the sum overall subgroups of A where it mapped surjectively. When you switch between these two sides, you can simply get the Mobius inversion for the lattice. And this is how you transform between homomorphism and surjective. So really, this Mobius function, you can just think of them as some big triangular matrix where you put an order on all the possible abelian subgroups inside A, and then it is where the entry is 1 or 0 depending on the belonging or not. And solving this triangular matrix back, that gives you the Mobius function. Okay. So, and when you do all subgroups homomorphism via the same way, you get the counting for abelian extensions that is surjective homomorphism. Okay. So this is definitely when the we are in the dreamland where everything holds exactly as what we expected. And our hope is to generalize this whole thing to all extensions, not necessarily abelian or non-abelian. And this is what we call our theories. The idea would be, okay, starting from now, it's going to be expectations, heuristic, whereas this is really truths. So we still wanted to mimic the thing we have done for abelian extensions, where we basically just form an Euler product where we can freely do whatever we want locally. And we needed to make some adaptations. When we form this local series for abelian extensions, you just need to use the star, which is the abelian universe for P part. But for general groups, the universe locally is, let's say, G is some permutation group, and we have some G extensions, which is a surjective map from GQ to G. Then how to extract the local information of this extension? You can just pick a choice of the decomposition group over P once and for all. And since we have seen that those wildly ramified case happens rarely, only one P dividing your size of the group, you can look at the tame universe of all the extensions, which is this very explicit generator later, and you look at maps from this group to G. This is all the possible G extension locally. And now, when we combine these local things to a global things, you are not allowed to choose arbitrarily. Like that will be simply too many. And how to understand this to go to global. So we still wanted to have some analog of that product expression. And although this is not even close to be true, that there are some theorem called Riemann existence theorem, but roughly speaking, our expectation is if you look at the S ramified extensions, then we hope that the inertial group as free product generates this group. Okay, this is not true, but will be close to our expectation. Okay, and then if you look at if you believe this model, then when you combine this local data to the global data, you are free to choose what you map to for these Y, which is the inertial group. But since these Frobenius is already secretly determined by how you map this one, so there is a chance whether your choice is legal or not. When you do all this local map gluing together, you don't know whether xy x inverse is exactly equal to y over p in your free product. And when you know nothing, you can just believe that there is a 1 over the size of g probability that this equality is hit. So that's why locally you say you just do all your local options, and then there is a 1 over the size of g possibility that this is a legal extension. And then when you combine these together, can form your generating series. Like this. When you count number of order for the book, that's equals 1 over. And that is just similarly as what we did before. Look at all the y. For each y, what that give you the minimal index, the contribution is the number of x dot x so remember we have this density that will still be happen here. Let's just say this from some stabilizer formula is going to tell you that this is a number of orbits for the sequence inside G, the index is minimal, where the action is the cyclotron action. Okay. You will need to manipulate this either with Y, and this is going to be the stabilizer over the size of the group, or you can look at the whole gamma group and this term with the term about Y is going to be the number of fixed point. So there are different approaches to look at this, but they're all going to give you that this is the number of the orbit for this cyclotomic action on this minimal index element on the easy class. So Malle's conjecture follow from, which is if you look at G, that is the permutation group transitive inside Sn, then the conjecture said that the number of G extensions is symptotically x to 1 over a and log x to the b minus 1, where a is the minimal index element for all element among all non-trivial elements inside your permutation group, and b is the size of the orbit where the index is minimum, where the action is from the absolute gamma group is just powering on the element via the cyclotonic character. And so I just want to comment that some of you probably know that there are some problems with this conjecture, but it is fine. And to fix, yes, and I don't want to talk too much about the examples today, but to fix all the issues, potential issues, this is perfect as long as you just stick to the set where, okay, you have all the previous conditions. But you don't allow your field to intersect with the cyclotron extensions. Okay, if you impose this extra condition, we are in the very nice world. Everything is consistent. You don't worry about potential problems. And yeah, so if we have more time, I will talk about the later story maybe on the last day. Thank you. Let's stop with. Yes.
What is the index of Y? What is that? I think I missed it.
Oh, index. Okay, this is something here, right? So we define that index to be the number. Did I write that? The index of a number of an element is a number of orbits inside Sn. Yes. So that is just I should definitely say more that for the general situation, you will still have that number of orbits is capturing the discriminant. Basically, you still write the discriminant as a product over all local like algebra, and for each one, that is the number of orbit within that orbit inside the equation. Yeah, so but the idea is very similar just to the Malle.
And what was GS?
This is highly heuristic. It is not true. This will be the approximate truth that we are trying to get. But except, okay, maybe at some key extensions, you have some theorem that is actually capturing this, but you will also need to modify the statement. But this is only a heuristic.
So the free product on the right hand side of the question.
Yes.
I understand like what that is. I don't know, like what does GS represent?
Oh,
Symbol.
this is okay. So this is the absolute Galois group for Q that is only ramified at S, and this will be the local inertia group of GQP. Yeah.
Thank you.
What do you change about the heuristic when you have a different base field?
That is a good question. So if you have different base field, then you just replace this by GK, and then there's nothing. Yeah, I definitely planned to do more carefully on these things because it has been asked a lot, but I don't have the time. So ask me, I will show you how to do these all the stabilizer to actually get the constant. But there is really no difference if you change your base field to general number field.
Questions? Thank you again.